Hey there, Dangar Stu here. Today's video is about making a fuel gauge for the boat using a pressure sender and is proudly sponsored by marineengine.com. About the middle of this video, I get a call from Shane at Coast Marine and we head up and have a look at the boat and find out what's going on there. But before we do that, let's start making this fuel gauge. Alright, if you're still here, let's dive in and have a look how we're going to make this fuel gauge. The two primary bits of gear we're going to need to make this fuel gauge is an Arduino, which we'll talk about in a minute, and a pressure sender. So essentially a gauge that senses pressure and sends it electronically to the Arduino. Okay, this is an Arduino and this is an Uno. There's various models, but this is a pretty basic model. Now these sell for like $17 Australian, so they're really cheap, probably like, 10 US at the moment. And essentially they are a little mini computer. They're specifically designed for these types of projects though, and they have a software library component and this hardware component. But they've got some really cool things, such as digital inputs and outputs and these analog inputs that we'll be using today. So this is the main little computer we're going to be using to drive our whole fuel gauge system. Now, you get these things called shields that plug into these Arduinos to expand them. This particular one is an LCD screen. Also has a couple of buttons, some sort of cursor keys, a reset and a select. So you could have menus and all sorts of stuff, which we may do down the track, but we're not going to use those keys for now. We're mostly interested in just the screen to display our fuel level. Now, we need to use a couple of the pins off the Arduino here. We're going to need to use a couple of the analog ins, one for each fuel tank, the 5-volt out and the ground. This shield plugs into this Arduino here. These pins just plug straight in. And we don't have sockets on the top. Quite often a shield will actually extend these sockets so you can continue to stack them. This one doesn't. When you're using Arduino shields like this, it's really important to understand which pins the shield itself uses, because you can't always use them again. Some of them you can, but not all. In this case, this shield uses analog input 0 to read the keys. It reads them as an analog input and it assigns a certain range of voltages to various keys so it knows which one you're pressing. Because of that, we can't use 0, it's already being used, so we'll use 1 for the port tank and 2 for the starboard tank. Although they don't have, the plug-in pin sockets on the top, what they do have are these little ports here we can solder onto, and they're connected to the pin opposite. So you can see here there's no little hole for A0 because it's used by the shield itself, but we are free to use 1 to 5 here. What I'm going to do is I'm going to take a couple of these jumpers. Normally these would just push into these type of sockets, but we don't have them, so I'm actually just going to solder them through the board here. Before we start playing with the actual pressure sensor I'm going to be using, I'm first going to wire it up with a simple potentiometer, a variable resistor, just so we can more easily test the display through a sort of range of readings. Okay, currently laptop's not even on, just getting power from the USB port. On these Arduinos there's also a little 9-volt input here, so ultimately I would power it from the battery just with a little step down transformer from 12 to 9 volts. Pretty easy to find. This is the pressure sensor I'm going to use. It apparently is, oil, fuel, water, everything resistant and, suitable. It's a G quarter thread, which I believe is a British parallel thread, and about 13 mil across I think it is. I don't know where the quarter comes from. I think it's something to do with the internal diameter of the pipe or something along those lines, 1/4 inch, even though it's obviously much bigger than 1/4 inch. But this has the same 3 wires, a sense wire, a positive and a negative. These work in very similar ways as far as I understand. This is a potentiometer, which is just a variable resistor, very similar to like the volume knob on your old stereo, that kind of thing. And these essentially work as variable voltage dividers because it varies the resistance as you turn it. Hang on, let me put this down. So as you turn it, it varies the resistance, and between your sender and positive gets greater and your sender and negative gets less. And so the amount of the incoming voltage that goes down your sense wire changes in proportion to those two resistances. Because I was using my dodgy old soldering iron, which was seriously rusty, couldn't tin it, it's pitted, it's rusty, it's awful, needs replacing is the short version. So what I've got is some really bad solder joints here, but it looks like what's happened is that there is some connectivity between A2 and A1. A2 is my port tank, A1 is my starboard tank, or vice versa. So at the moment you can see I've got the variable resistor set all the way one way. Which way? This way. So it's saying we have nothing left in the port tank and a little bit left in the starboard tank. Now if I short these two pins, we'll end up with 0 in both tanks. And that's because both tanks are reading from the same sensor. But if I now turn the potentiometer, you can see my port tank's going up, but so is the starboard tank, and that's because of the bleed across. It's not the same value because they're not completely shorted, but that's a sign of a bad connection. So with this on full, we get 123. On minimum, we get 0. That's the range we've got for the maximum minimum on this potentiometer. The exact same principle applies, except we can use this pressure sensor. Now the pressure increases as the tank fills because just the weight of the diesel pushing down on the sensor. Because of the shape of the tank, that won't be a linear relationship. There won't be, you know, say we're getting a value of 0 when it's empty and 50 at 100 litres and 100 at 200 litres. It won't be that sort of that simple, unfortunately. We may be able to do some little formula that approximates it. Otherwise, we're going to have to sort of map it with a table or something like that. Now, the reason I've tested it with this potentiometer is it's just nice and easy to move it around. What I'm going to have to do now is rig up some way of testing this sensor. I can test my pressure sensor pretty easily if I can physically rig something up to hold water, because the shape of the tank doesn't make much difference. You can have quite a thin column of water, you know, think diesel, but we'll use water. And it doesn't matter if it's thin or it's a metre wide, the pressure's the same on the sensor. So we should be able to get some rough idea about what our minimum and maximum value is going to be. Now, it's pretty important to get some sense of what our maximum value is likely to be, because if we end up having an empty tank be 0 and a full tank being, say, 36 out of 1,023, we don't have a very good resolution on how full our tank is. And what we need to do to fix that is, instead of saying go from 0 to 5 volts, we can say actually scale it on 0 to 1 volt or something like this, which will bring it so that when the tank's full, it's as close as possible to that maximum value, that 1,023. And that's what we want to achieve to give ourselves the most accurate reading. All right, now there's some pipe down here in the garden. Looks too big, looks too big. You guys know where it is? Copper pipe. Where's copper pipe? Maybe even copper pipe's going to be too small. Oh, look at you all there. Okay. Aluminium pipe. Steel pipe. Oh, that's pretty close. Let's have a look at this. Ooh, don't even know what that is. Oh, it's the stand from an old lamp. Wow. What are the chances of that? Whenever I tell you I'm never lucky, this lamp actually, it's an old curved lamp head, used to pivot like this, but the thread in the end is exactly the thread in this sender. Wow. Okay, so these aren't tapered. So generally what you do is put a bit of an O-ring, either a crush olive or something at the front here, but we might try just an O-ring around the base here. But what I will do first is, now will I? No, it's open there, that's a shame. Look, what this will probably give us some sense of, I think it's a linear relationship as it gets taller, i.e. a foot of pressure, which is about what we've got here, should give half the reading that 2 foot would. So what's this end? Threaded? No. So I think what we'll do is we'll just cut it here and then see what kind of reading we get. Is it, 1 out of 1,023, or is it 2, 10, 20? I don't know. I'm expecting it to be quite low, because when you imagine the amount of pressure that the weight of a metre or two of diesel gives compared to, say, I don't know, say oil pressure sender, in an engine, we might find we're talking at a really, really, really small scale, which could be an issue. Okay, O-ring round the base, a little bit of sealant on the thread. Oops. Okay, should work. Now, next job, let's swap out a potentiometer for this pressure sensor. Just soldered these directly wire to wire. Just put a little bit of tape on so they don't short against each other, which they could very easily do right now, particularly given they're all the same length. Alright, let's fire it back up. Oh, so one thing I probably haven't explained so far is that you write the software on your laptop using the IDE that Arduino provide as a part of the whole sort of suite. You upload it to your little Arduino Uno, and then from that point onwards, the code actually lives on here. As soon as you give it power again, it just boots straight back up into that bit of software. Okay, so at the moment, we've got a reading of 100. Now, there's no real pressure other than atmospheric pressure on that sender, so 100 may be 0, 100 may be 1 atmosphere of pressure. So if we just blow in the end here, blowing reasonably hard, got it from 99 to like 103. So we may find that, we may actually need a different type of pressure sensor, something that's designed to be more sensitive, have a smaller range of pressure, but I don't know what pressure I was really putting in there. So let's just fill it with fluid, see if we get any change in reading at all. Okay, now let's go a little funnel. I wish our pipe was a bit taller, but is what it is. So, interesting. Went from 99 to 101, so very small change. Ignore that starboard tank. But it's about the same change as when I was blowing in it reasonably hard. So, interesting to see how much pressure 1 foot of water gives you. Actually, I should measure it. It's probably not even a foot, is it? Oh yeah, pretty much dead on a foot. 300 mils. So far so good. Now, there's one thing we can do to the code to help with that a little bit before we get into a hardware fix. Phone just rang. Shane at Coast Marines pulled the boat out of the water. He said there's a lot of growth on the prop, which we sort of saw when we went for the dive. So let's jump in Red Dwarf and head up there and take a look. Plenty of growth on the prop. Shane actually thinks this is the bulk of the problem. Anodes are getting eaten, but not gone, which is good. Back from seeing Shane and Mick up at Coast Marine now. So, prop was very dirty, dirtier than I actually thought. When I went for that dive, it was really poor vis, and I thought it was mostly weed, which obviously when I spun the prop came off. But lots of barnacles still, which Shane's pretty confident will be throwing the balance out pretty badly. What they were also saying, which another couple of viewers commented as well, is that where the gearbox flange comes onto the polyflex coupling, there's no spigot that centers it, so it's all against the bolts. So as it rotates, you know, it can go out of alignment, and, you know, 0.5 millimetre is 20 thousandths, and we're trying to get it under 5 thousandths, so it can put it out a fair bit. So the plan is clean the prop, going to put some prop speed on it while it's there, also going to spray paint another couple of coats of anti-foul, because those first few coats were rolled on. It's thinner when you roll, for one, and you really do want to start building coats of anti-foul up. You don't remove it all and put new on, you just keep kind of layering it up. Get what's flaking off, because you don't want your new anti-foul to flake off, but, you know, essentially you give it a good pressure wash, let it dry, put more on. So that's what we're going to do while it's out. Technically, that anti-foul has actually been on about 8 months now, so it's kind of due anyway, and I would like to get those coats building up sooner rather than later. So, clean the prop, make a new coupling, refine the alignment. The other bit of good news from my point of view is that Shane said the alignment actually wasn't that far out, which is kind of nice to know that it was sort of getting there. I took it to those guys because I felt that the amount of vibration was disproportionate to how close I felt the alignment was, so maybe something else was up. And it looks like there are a couple of other things. Definitely the prop clean, definitely getting to the point where the gearbox flange, the coupler, and the gearbox itself are all centered on spigots. So we're going to fix all those things and see how it goes afterwards. Anyway, let's get back to our fuel gauge. All right, let's have a quick look at the code that we've got running on the Arduino to drive our fuel gauges. It's not that complicated. I started this program using a default template that came with the liquid crystal display. This defines some pins, some digital pins that the Arduino talks to the display with, and essentially calls an initializer for it. Then in the setup routine, this is a routine that only gets run once when the Arduino gets turned on or reset, and it's all pretty much to do with setting up the LCD screen. Because I only update the values, I write the text, port tank, starboard tank, with a bit of cursor positioning information just to get it nice for use tabs. This only happens once as well. So here we put the cursor top left, just print port tank on the screen, move it down one line to the left, right starboard tank. So pretty straightforward. Now, as you saw, the value for empty to full on our little tube went from about 99 to, say, 104 or something. And that's proportional to a reference voltage of 5 volts. There's another command we can use, which is analog reference, and we can pass it internal. And this will actually set it to 1 point. So, where are we? So this will set, actually, set reference voltage to, keyboard's terrible in these computers, 1.1 volts. This should give us a much higher resolution on the readings we're getting, even for such a short tube. You can supply an external reference voltage, at which point you say external, and then we have to have a little circuit to supply that voltage to a particular pin, but we're going to try this for now. All right, all I need to do now is send this over to the Arduino, so I'll plug it in again. And then as soon as I do this little arrow pointing to the right, it will compile this code, upload it. Oh, nice error. Analog reference not declared in this. I wonder if there's a library for this. Oh, there we go. American spelling. Analog reference, there we go. Compile that. And as soon as it says done uploading, we now have the latest version running on the Arduino. All right, the tube's pretty empty now, and we've gone up from 99 to 466, which kind of makes sense. We've gone from a 5 volt reference voltage to a 1.1. So what we need to do now is see what it comes up to when we fill the tube again. All right, so 465. up to 476. So before, empty to full gave us a resolution of about 4 digits, which meant that we could really just, the best we could say is whether it's quarter full, half full, 3/4 full, whatever. Now we've gone to about 10, so we can actually say within 10% what we think it'll be. This may end up being quite a good reference voltage by the time we have a tube that's about 1.5 meters long. Now I'm going to add one more function to our little program, and what we're going to do is we're going to map the values we're getting. We're going to call 465, 0, and we're going to call, say, 480, 100%. Gives us a little bit of wiggle room at each end so we don't go off the scale, but we'll do that, and then we'll call it a percentage, and, you know, we'll see what it looks like then. At the moment, we say the value for the port tank is simply an analog read off pin 1, which we've defined up here as port tank, just to increase readability. But what I'm going to do now is do a map function. I'm going to pass in the result of that analog read, and we're going to say that we're going to map, what did I say now, 465, and then we're going to map that from 0 to 100. And so this is the range we're actually getting from the analog read, and we're going to map it to 0 to 100. All right, let's run that, see what happens. So here you can see port tanks hovering around 66, 80, 73. Obviously that's the jump for each integer, 93. There we go. So let's empty it and see what it goes down to. Alright, hovering around, you know, high as 20, as low as 3, I think was the lowest, 6, sorry. So 6 to 20 is about what it gets to. So, yeah, about halfway. So, looks like it's working, theoretically. You can see the starboard tank's just an ungrounded pin at the moment, giving a nonsensical reading, but that's okay. Obviously, the next issue to solve is the accuracy, and this is really fine-tuning. I think we've sort of got a successful proof of concept now. We just need to fine-tune a few things. Look, it could actually be fine the way it is, because this tube's only 1 foot tall, and we're getting, you know, I think we're getting, what was it, about 10 graduations in that tube, and it fluctuates about 3 around a particular reading. But if you consider that that's probably about 20% of the height of the actual fuel tank, then we're actually going to get a reading about 5 times more accurate than that. Then we've also got the option of doing a few other things, fine-tuning our reference voltage a little bit more, but also potentially finding a pressure sender or a pressure sensor that is more sensitive. We really need to go from atmospheric pressure to, say, 1.2 atmospheres or something. So if we can find a pressure sender that's more tailored to work in that kind of range, we're going to get a better reading as well. So the few things we can tune, but I do believe this, even as it is reasonably useful. We'll see. Anyway, interesting experiment. Not our usual fare on this channel, as you know, so those of you that are still watching at this point and haven't given up in disgust, thanks for sticking along. Hope you enjoyed. And I'll catch you next week when hopefully we'll be getting the boat back. All right, well, take care. I'll catch you then. See ya. You're going slippery sliding, are you, Dotty? Oh, look at your leg, Daffy. Be careful. It might look a little bit ungainly, but the good news is Daffy's starting to use her broken leg to scratch again for the first time in ages, so that's good.